Hey folks, welcome to your final set of Chemistry 1 video notes. Today, in our second and final lesson of our 8th and final unit, we'll be talking about the gas laws. In this lesson, we'll be covering standard C.4.4, C.5.1, C.5.2, and C.5.3, which ask you to apply the mole concept to determine different quantitative measurements of a gas at standard temperature and pressure. Use the combined and ideal gas laws to explain changes in volume, pressure, moles, and temperature of a gas. Use the ideal gas law to calculate the changes in volume, pressure, moles, and temperature of a gas. And use all of those skills together to calculate the volume of the gas at different conditions, based on its balanced equation and lab data. That's a lot to learn for one set of notes, but we can't finish if we don't get started, so let's go. As we talk about gases today, we're going to talk about different measurements of a gas, such as its volume, number of moles, temperature, and pressure. Pressure is the only one of those variables you haven't learned about so far this year. Pressure is defined as the force exerted on a given area, or P equals F divided by A. It's dependent on how much force is being applied and the size of the area the force is being applied to. We can measure pressure in a number of ways. In physics, we often use the Pascal, which is equivalent to how many newtons of force are being applied to a square meter. 1,000 pascals is, of course, a kilopascal. If you've ever checked your tire pressure with a traditional tire gauge, you've probably seen kPa before, but have largely ignored it because here in America, we use PSI, or pounds per square inch. Why? Because for some reason, ourselves and 2 other countries seem to hate the metric system and haven't converted to it yet. At sea level, the air pressure in PSI is about 14.7. The atmosphere, or ATM, which we'll use most often in our calculations today, is equal to 101,325 pascals, 101.325 kilopascals, or 760 torr. 1 bar equals 100,000 pascals. 1 inch of mercury equals 3,386 pascals. 1 torr is 1/760th of an atmosphere, and a millimeter of mercury is equal to 1 torr. Phew, that is a lot of different units and conversion factors for pressure. At some point in your chemistry journey, you'll be asked to convert between these different units and use them to figure out the other 3 variables. But for now, we're just going to stay focused on the ATM, or atmosphere. Let's talk about how each of these 4 variables are related to each other. Around the year 1700, a guy named Guillaume Amonton, pardon my French, was the first to find evidence for the relationship between the pressure and temperature of a gas. About 100 years later, Joseph Louis Gay-Lussac determined the relationship even more precisely. For that reason, the relationship between pressure and temperature has 2 names, Amonton's law or Gay-Lussac's law. In either case, the general idea is that the pressure is directly proportional to the temperature, assuming that you keep the volume and the number of moles constant. So what does directly proportional mean? Well, if one goes up, the other one goes up as well. If one goes down, the other goes down. What does that look like experimentally? Well, imagine you take a round-bottomed flask filled with a gas and stopper it on the end with a pressure gauge at the top. You set that flask inside of a beaker of water, what we chemists call a water bath, that's sitting on a hot plate. When the hot plate is off, the pressure is pretty low. If you turn the hot plate on medium, the water warms up, increasing the temperature of the gas inside the flask, and then the pressure increases as well. If you put the hot plate on high, the pressure increases even more, because the temperature increases. If we were to take multiple data points from this experiment, we might form a graph that looks like this. As you follow the graph, as one of those variables increases, so does the other. So, with this relationship, we can create a useful equation. If we know that the number of moles and the volume stays constant for any gas, we can predict what the pressure would be under a different temperature condition. We'll call these conditions 1, our initial condition, and condition 2, what the measurement changes to, or our final condition. This is just like setting up a proportion in math. The equation is P1 over T1 equals P2 over T2. So if you know any 3 of those, you can find the 4th. The relationship between volume and temperature is the same as the relationship between pressure and temperature. Charles's law states that if the pressure and number of moles is kept constant, the volume is directly proportional to the temperature. Again, if one of these increases, the other increases, or if one decreases, the other decreases. Experimentally, you could take a balloon and fill it up with a gas. If no gas can escape from the balloon, and you hold the pressure constant, you can place that balloon in cold water, and the balloon should decrease in size. Or if you place it in warm water, it should increase in size. This gives us a very similar looking graph and equation to the one we just saw a minute ago. For Charles's law, the equation is V1 over T1 equals V2 over T2, where the 1's are the initial volume and temperature, and the 2's are the volume and temperature after one of those variables changes. Again, if you know 3 of those values, you can find the 4th. The relationship between pressure and volume is a bit different though. Boyle's law says that if you keep the temperature and the number of moles constant, the pressure is inversely proportional to the volume. In other words, if the pressure or volume increases, then the other one decreases. We can see this experimentally with a sealed syringe of air. If we have a pressure gauge attached to the end of the syringe, we can measure the pressure as we push the plunger in or pull the plunger out. As we push the plunger in, if we keep the temperature the same, we'll be decreasing the volume and will show an increase in the pressure. The opposite is true when you pull the plunger out. This data would give you a graph that looks like an exponential graph. We don't like exponential relationships in chemistry because that's just too much math. We like linear relationships, like the 2 graphs you've seen before. So to turn our exponential graph into a linear graph, instead of graphing the pressure versus the volume, we graph 1 over the pressure versus the volume. This gives us the graph on the far right and shows that the volume is directly related to 1 over the pressure, meaning that the pressure and volume are inversely proportional. This gives us a different looking equation as well. This equation is P1 times V1 equals P2 times V2, where P1 and V1 are the pressure and volume of our gas initially, and P2 and V2 are the pressure and volume of our gas after we change one of those 2 variables. Similar to our other relationships though, if we know 3 of these values, we can find the value of the 4th. Our last relationship we'll look at today is that between volume and the number of moles. Surprise, surprise, the mole is involved, and so is Amedeo Avogadro. Avogadro's law says that if we keep the pressure and temperature the same, the volume is directly proportional to the number of moles. Think about this in terms of blowing up a balloon. As you add more air, thusly more moles of your gas, the balloon increases in size, or the volume increases. The equation for this relationship is V1 over N1 equals V2 over N2, where V1 and N1 are the volume and number of moles of our gas initially, and V2 and N2 are the volume and number of moles of our gas after we change one of those 2 variables. Just like all the relationships before, you can find the 4th variable if you know the value of the other 3. So if we combine all of these relationships together, we get what's called the ideal gas law. The ideal gas law is useful when we have a gas that behaves ideally. We'll talk about what that means later. And we have the ability to measure 3 of the 4 variables, but can't seem to find a way to measure the 4th. For instance, if you run an experiment with an ideal gas and have the tools to measure pressure, temperature, and volume, you might not be able to measure the number of moles. The ideal gas law will help with that. The equation reads PV equals nRT, where pressure is measured in atmospheres, volume is measured in liters, N is the number of moles, that's measured in moles, and T is the temperature measured in Kelvin. If you don't remember, in order to find Kelvin, you take the Celsius temperature and add 273.15. So 20 degrees Celsius would be 293.15 Kelvin. You might have noticed I glossed right over that capital R there. That R isn't a variable like P, V, N, or T. It's a constant. It's called the ideal gas constant. For our purposes, we're going to stick with that constant being 0.0821 liter atmospheres per mole Kelvin. That weird unit helps us to cancel out the units as we're completing the equation. R is a constant. As you're doing the ideal gas law problems and writing down the value of each of these 5 pieces of information, you can automatically, every single time, write down R equals 0.0821 liter atmosphere per mole K. For the rest of these 4 variables, you have to read them in the problem. You'll start off with some easier problems where I give you 3 of those variables with correct units, But as you get more familiar with this, you might be expected to convert, say, Celsius to Kelvin, or milliliters to liters. Later on in your chemistry journey, you'll be expected to do even more conversions than that. To use the ideal gas law, you'll be given 3 variables. You just have to algebraically solve for the 4th. Normally I'd do some examples here, but this set of notes is already going to be running long, and this is just basic algebra, which you should know how to do by now. If you can read the story problem, figure out which number in the problem goes with which variable, then plug and chug, you should be fine. If you're doing an experiment with an ideal gas at 2 different sets of conditions, you could use what we call the combined gas law. The combined gas law requires that the number of moles for the ideal gas be held constant. Since R already is a constant, no matter the conditions, we can cancel out R right away. Then if we solve for N in the ideal gas law, we'd get PV over T. Therefore, since the number of moles in one set of conditions is equal to the number of moles in the other set of conditions, we could set up PV over T for one set of conditions equal to PV over T for the second set. In other words, P1V1 over T1 will be equal to P2V2 over T2. An example of this would be if you were given the volume, pressure, and temperature of a gas at one set of conditions, and then given 2 of those variables for the same gas at a different set of conditions, and then you can easily find the third from there. You could do this using only the ideal gas law, but using the combined gas law saves you a number of steps. So we've seen how the volume can change based on the temperature, pressure, or number of moles in a gas. If we want to compare 2 gases that have the same number of moles, that's kind of hard to do, because with any little change in pressure or temperature, the volume of a gas changes greatly. Our solution to that is STP, or standard temperature and pressure. This is a pressure and temperature that chemists agree on for comparing different gases. It's the same across the world, and many times the calculations we end up doing are done at STP. So if you're doing an ideal or combined gas law problem, and in that problem it says the gas is at STP, that means the temperature is 273.15 Kelvin, and the pressure is 1 atm. The beauty of ideal gases and STP is that for any gas, no matter what gas it is, 1 mole of that gas at STP has a volume of 22.4 liters, no matter what. This is known as the standard molar volume. In our stoichiometry lesson, you were able to use limiting reactants, molar masses, Avogadro's number, and other information to figure out how many moles, particles, or grams of a substance you'd have based on that info and your balanced chemical equation. STP just adds one more conversion to your toolbox of conversions. Say you did a stoich problem and found out that you produced 4 moles of carbon dioxide. If you wanted to know the volume of CO2 produced at STP, you'd simply multiply 4 by 22.4, because for every 1 mole, you have 22.4 liters at STP. Okay, we're in the home stretch now. The kinetic molecular theory is a simple, microscopic model that explains the behavior of an ideal gas. In other words, the 5 postulates that I'm about to read explain what it means for a gas to act ideally. Number 1. Gases are composed of molecules that are in constant, continuous, random motion. They travel in straight lines and only change directions if they hit each other or the walls of the container they're in. Number 2. The size of the gas molecules are extremely small compared to the vast distances between them. Number 3. The pressure exerted by a gas inside of a container results from the gas molecules colliding with the walls of that container. Number 4. The collisions of gas molecules are perfectly elastic. This means that when a gas molecule collides with another gas molecule or the walls of its container, there's energy transferred from that molecule to the thing it collided with. But when that happens, none of that energy is lost to sound or heat. Finally, number 5. The average kinetic energy of the gas molecules is proportional to the Kelvin temperature of the gas. In other words, the higher the temperature, the faster the gas molecules move. So at this point, you're probably thinking, how does the kinetic molecular theory help me understand the behavior of gases? That's a great question. Up to now, you've only dealt with the mathematical relationships between the different properties of a gas. Using the kinetic molecular theory, we can understand these relationships conceptually, not just mathematically. So, Gay-Lussac's law said that temperature and volume are directly proportional. Why is that? According to postulate number 5 of the kinetic molecular theory, temperature is directly related to the average speed, or kinetic energy of the gas molecules. So if we increase the temperature, our gas molecules will be moving faster. According to postulate number 3, the pressure of a gas is based on the force and frequency of collisions between gas molecules and the walls of their container. So if we increase the temperature, which increases the speed of gas particles, they'll hit the walls of the container more often and with more force, meaning that we also have an increase in the pressure. Charles's law said that if we increase the temperature, we have to increase the volume in order to keep the pressure the same. Remember that pressure is the amount of force applied to a certain area. If we increase the size of that surface area that the force is being applied to, we effectively decrease the pressure, because there's less force being applied per unit area. In the last slide, we said that an increase in temperature increases the pressure because our particles are moving faster. But for Charles's law, we're wanting to keep the pressure the same. To do that, we'd have to increase the surface area of the container walls. In other words, in order to keep the pressure constant when we increase the temperature, we'll have to increase the volume so that our faster moving molecules hit the walls of the container over a larger area. Avogadro's law said that if we have more molecules of a gas, our volume will increase if we keep the pressure the same. This is a similar reasoning to what we just described in the last slide. If we add more particles, we're bound to have a higher frequency of collisions. If we want to keep the pressure the same as we're adding more particles, we'll have to increase the surface area of the walls of the container in order to spread out those collisions more. In other words, if we want to keep the pressure and temperature constant as we add more molecules of a gas, we have to increase the volume. Finally, Boyle's law said that the pressure and volume are inversely proportional. When we increase one, the other decreases. If you decrease the volume, you're decreasing the surface area of the container walls. When you do that, you cause a higher frequency of collisions. When you have a higher frequency of collisions, you have a higher pressure. Therefore, decreasing the volume increases the pressure. Well, that's all for today, folks. I know it's a lot to take in, but over the next few assignments, we're going to have a chance to see these gas particles in action and visualize the concepts so that we understand them conceptually before we start using them mathematically. With enough time and practice, you'll be experts in the standards I mentioned at the beginning of this video. As always, if you have any questions, please let me know.